Okay, good morning. Got our exam number 2 tomorrow, right? Yes. So we will do a lot of reviewing today for that. And I've got a bunch of poll questions set up, so I think it'll be a good review. Okay, let's get right into it. So here's our first question. A block sits at rest on a frictionless surface. Which of the following sketches most closely resembles the correct free body diagram? Each red arrow represents a force. Question about free body diagrams. Hold on, I'll do a poll here. Here, I'll start the poll. Hold on. Poll number 1. There we are. Question about free body diagrams. F or N. I mean, you can use whatever you want. What you want is so that when you look at that free body, see, if you just use F for every force, you're going to look at your free body diagram and you're going to see 4 arrows with Fs on them, and it's not going to really tell you anything. But if you look at your free body diagram, you see one has an N, oh, that's a normal force. One has a lowercase f, oh, that's friction. One has a T, oh, that's the rope, the tension in the rope. One has a F sub G or a W or an mg, however you like to use for weight, the force of gravity, then you know that's the force of gravity. So if you use something that's meaningful to you, so that when you look at that free body diagram, it tells you something more than just there's a force, 4 forces acting on my object. When you look at it, you know what those 4 forces are. That's the key. So you want it to be useful for you. So use whatever symbol you want. Sometimes it's tricky because you've got something weird, like a surface is easy. You got a normal force and you've got friction force. Gravity is easy. We got the force of gravity. A rope is easy. You've got tension. Sometimes you have a hand pushing on something. How do you mark that? Is it F hand? Is it a normal force from the hand? It's up to you. Whatever helps you get that free body diagram right, and then use that free body diagram to get the next part right. That's what it's all about. Okay, everybody had A as their answer. That's exciting because that is the correct answer. You knew that it was sitting on a frictionless surface. So if there was any horizontal force, the box would be moving. And how should I do this? I guess I'll just circle them. Then you won't be able to look at them later. Maybe I'll hide. Where can I hide the answer here? I'll put the answers over here. Okay. Next one. Same block. Now it's moving with constant velocity to the right on the same frictionless surface, which best represents the free body diagram. Okay, it looks like the leading answer was B, but of course that cannot be the case, because if there was a net force to the right, this is telling us there's a net force to the right, then there would have to be acceleration to the right. And what does it tell us up here? It's moving with constant velocity, no acceleration to the right. So what's the correct answer? A. A is the correct answer. If there was friction, then maybe we would be dealing with E here, right? The friction would be slowing it down. You would have to have some force to the right to keep it moving. But with no friction, you just give this thing a push, you let go, and it's going to keep moving forever until a force acts on it and stops it or changes its motion, because it has inertia. So I'll put the answer down over here so that people can look later. All right, next one. Let's see. We started off well, but we slipped a little bit on that one. Okay, you're awake now, though, right? Same blocks. Constant velocity to the right on a surface that has friction. Oh no, I let it out of the bag. So again, the block, listen to what they're saying. The block is moving to the right. The surface has friction. Pick the free body diagram. What would the block be doing if it was sliding to the right and there was friction there? This is a different question than the previous one. This doesn't tell us anything about the acceleration of the block. Just says it's moving. Oh, it does say it's moving with constant velocity. Yeah. Constant velocity to the right on a surface that has friction. Okay, so I had already mentioned in the previous one that if it's moving at constant velocity, that automatically rules out those, right? Because those have a net force in the horizontal direction. There's acceleration. And if there's friction pointing one direction, then we would have to be pushing in the other direction to keep it moving. We know that there's a normal force and a gravity for sure, so that rules that one out. So D would be our best answer here. Okay. And most of you got that. That's good. Back on track. Tom pushes two identical blocks on a horizontal frictionless table from the left. The force that block 1 exerts on block 2 is F12. The force that block 2 exerts on block 1 is F21. Compare the magnitudes of those two forces. Okay, good. So most people said number 2, which is correct. The boxes are accelerating to the right because of that push, right? But that doesn't matter. When 1 pushes on 2, 2 pushes back on 1 with an equal and opposite force. It doesn't matter if the boxes are at rest, if they're moving with constant speed, if they're accelerating, none of that matters. Anytime 2 objects are interacting with each other, they exert equal and opposite forces on each other. Okay, next one. Same scenario, pushing 2 identical boxes, horizontal frictionless table. The force block 1 exerts on block 2 is F12. Compare the magnitude of F12 to F left. F12 and F left. Think about what's being accelerated by those forces. Okay. So think about what's being accelerated by those forces. F left is causing what to accelerate? F12 is causing what to accelerate? They're both accelerating at the same rate. Let's do it again. So which one has to be bigger? Or would they be the same? That's the situation, right? The force from block 1 on block 2 is causing block 2 to accelerate to the right. If the accelerations are the same, they are, right? Block 1 and 2 move together. The accelerations are the same. Okay, good. We convinced a few people to switch over. The accelerations are the same, right? Those 2 blocks are moving together. So the left force is causing both blocks to move. So it has to be twice as big as F12. F12 is only causing one block to accelerate to the right. Okay. Let's see. Let's try this one. So we've got 8 blocks, 8 identical blocks, frictionless table. The force that block 1 exerts on block 2 is F12. The force that block 7 exerts on block 8 is F78. What's the ratio of F12 to F78? This is pole 6. Which one has to be bigger? So the force from block 1 on block 2 is causing 7 blocks to accelerate to the right. The force of block 7 on block 8 is causing 1 block to accelerate to the right, and they're all accelerating at the same rate. So the force 1, 2 has to be 7 times bigger than the other force. F equals ma. If the accelerations are the same and one mass is 7 times more than the other mass, then the force has to be 7 times greater. Okay. Let's see. Let's work on some pulleys. Okay, so we lift the box up. The box weighs 1,000 newtons. Lift it up just a little off the ground and hold it there. With what force does he have to pull on the rope to hold the box off the ground? Okay, good. So you could draw a free body diagram for this object if you wanted to. You have the force of gravity pulling down. That's 1,000 newtons. And you have the tension in the string pulling up. And is that box going anywhere? No, it's just hanging there. That means the acceleration is 0. So sum of the forces equals ma. The sum of the forces is 0. So the tension has to equal 1,000 newtons. That means that the tension is the same everywhere in that rope. And the force over here has to be 1,000 newtons. Okay, let's make it a little more interesting. Lift that box up off the ground a little bit and hold it there. What force is required? Okay. So again, what does the tension in the rope have to be? Same situation, right? We could draw a free body diagram for that weight, hanging weight. The tension has to be 1,000 newtons. So the tension is the same everywhere on the rope. If the tension here is 1,000, tension over here is 1,000. So there's a pulling force in this direction of 1,000 newtons. That means there has to be a pulling force in the other direction of 1,000 newtons. Okay. The angle does not matter because the person is pulling in line with the rope. So in the previous case, the tension was in this direction and the person was pulling in the opposite direction, right? In line with the rope. And now the tension is in this direction and the person is pulling in this direction. It doesn't matter. The pulley just changes the direction, doesn't do anything else. Okay, how about this one? The rope is anchored at one end and the person pulls down on the rope in the middle a little bit to lift the weight up off the ground. What force does he have to pull on that rope with to lift that weight off the ground? You might have to do a little thinking here, a little calculation. The person is pulling straight down on the rope. Draw a free body diagram for this point right here. Draw a free body diagram for that point. Probably have to do some calculations. Okay, those are the tensions. Those are supposed to go to the same point, but that's okay. And what else do we have acting on it? The force of the hand, right? Pulling down. And we know what the tension in the rope is, right? What's the tension in the rope? Same as before, right? 1,000. Question about mechanical advantage. We'll get to that in a minute. So tension in the rope, we know, right? We know that 1,000. So let's redraw this. I'm going to move it over a little bit. Let's redraw this. We've got our object, our fist here, whatever that is, right? Fist, knot, pulling force down. We've got T cosine 5 degrees and T sine 5 degrees. So what does the pulling force have to equal? Is anything moving? No. So the pulling force the sum of these forces has to be 0, right? So we have F is equal to 2t sine 5 degrees. T is 1,000, 174. Okay. Yeah, 2 tensions, 1 on each side. Good? We'll move on. Okay, now we have this configuration. Pulleys. What force does he have to pull down on that rope attached to the small pulley to lift that box off the ground? This is number 10. You should probably draw a free body diagram for the small pulley. So Tension. What's the tension in that rope? 1,000 newtons, right? That's what's holding up the box. And the tension is the same everywhere in the rope. And we have the rope is pulling up on each side of the small pulley. So if you'd look at a free body diagram, it would look like what I drew here. So we have two tensions, 2,000 newtons pulling up on the small pulley. So the person would have to pull down with 2,000 newtons to hold it there. So there was a question about mechanical advantage. This is mechanical advantage, right? It's not the fact that the pulley has friction or not. When you only have one pulley, if usually it's just changing the direction of the force, not always, but usually that's what it's doing. You could, I guess you could get mechanical advantage with one pulley if you tied it up to the ceiling like this one is. But anyway, usually you have multiple pulleys when you get mechanical advantage. But the key is, look at how much distance something moves. So in this case, when the person pulls down 1 meter on the pulley, when the little pulley moves down 1 meter, the box goes up 2 meters. Okay, that's kind of the key to mechanical advantage. In all the cases we've had up till now, when the person pulled 1 meter, come on, what's going on? There we go. So in this case, if the person pulled 1 meter here, the box goes up 1 meter here. So that tells you there's a 1-to-1. That means that whatever force the person puts in, the box is going to feel the same force. The accelerations are going to be the same. Everything's the same. The velocities would be the same. Same here. When the person pulls 1 meter here, the box goes up 1 meter. If the person is pulling their hand at 1 meter per second, the box is moving at 1 meter per second. If the person's hand is accelerating at 1 meter per second squared, the box is accelerating at 1 meter. They're all linked, and so the forces are linked also. Same, this one is different though, right? Because when the person's hand goes down 1 meter, the box doesn't go up by 1 meter, right? Something is off here. So you'd have to figure out what it's taking. So the, I think the box would go up much less than 1 meter in this case. So that tells you that the person doesn't have to put in as much force. This one's hard to tell though. But this one's pretty straightforward. When this goes down 1 meter, 1 meter of rope goes up the other side and 1 meter comes down here. So actually what ends up happening is this goes up 2 meters. Sorry, half a meter. Half a meter. Because you end up with part of the rope comes from one side, part of the rope comes from the other side. You get a half from here and a half from there is one way to think of it. So the person's hand has to go 1 meter. No, I've got it backwards. When the person's hand goes 1 meter, the box goes up 2 meters. And because of that, the person has to put in twice as much force. When this goes 1 meter, this goes 2 meters. It's a little hard to tell sometimes. And so because of that, the person has to put in twice as much force. So you might ask yourself, why would a person want to hook up a pulley like this where they have to put in twice as much weight as the box? They have to exert a force twice as much as the weight of the box. They could have just lifted the box straight up with the force of 1,000, but they have to put in a force of 2,000 to lift the box up. Why would you do that? Because you can get the box to move twice the distance. Maybe that's important to you. You can get it moving twice the distance and twice the speed. So that's kind of a reverse mechanical advantage. Normally, when we think mechanical advantage, we're thinking about putting in less force and moving a heavy object like the jack on your car or something. So if you reverse the box and the person here, if you put the box hanging over here and the person standing over here pulling on the rope, then you can see that when the person pulls down by 1 meter, I think this is a little more clear, the box only goes up by half a meter. So the person would be putting in half the weight of the box here. And you can tell by counting the strings here, right? So here we're pulling up two times, whatever force the person is pulling on the rope, that's the tension in the rope. You have 2 of them acting on that pulley, pulling it up. So you get mechanical advantage in that case. Okay. So we'll talk more about this when we get to work. Work is force times distance. Go ahead. Question?
No, that was an accident. Sorry.
Okay, no problem. So when we get to work, we'll see that you don't get something for nothing, right? So if you want to lift a 1,000 Newton box with a 500 Newton force, you have to apply that force through twice the distance that the box moves, right? We're going to learn that next week. But that's where mechanical advantage comes in, is with the number of pulleys and counting the strings. So you can see right here, we have 2 forces up and only 1 down. So you can lift something. So if you're looking at these forces, they can be half as much as this one, right? Because there's 2 of them there. Okay. Let's look at the next one. What do we? Oh, we've got, application of the day. We've got a lot of applications for circular motion. One of them is banked question about this one. Yeah, it's much easier to move. So here, so let's just look at the tensions, right? We have 1,000 newtons tension in the string, 1,000 newtons, 1,000 newtons. The tension is the same everywhere in this string, right? Everywhere in that string, in that rope, the tension is the same. So we have 1,000. So on our small pulley, we have 2,000 newtons pushing up. Pulling up. So what force does he have to pull down to keep that pulley from moving? 2,000 newtons. Just to hold the 1,000 Newton block off the ground, the person has to put in 2,000 newtons of force. Now let's switch them. We have a rope. So now we have the pulling force, right? Whatever force the person's pulling with, that's the tension in the rope, right? So we have 2 times the pulling force up, 1, 2. And we have the weight of the object down 1,000 newtons. So the pulling force only has to equal 500 newtons in this case. You switch the person and the box, and now you have this mechanical advantage that gives you the ability to lift a 1,000 Newton box with a 500 Newton force. If you switch them back, you have the ability to move a 1,000 Newton box with a 2,000 Newton force, but you have the ability to move it through twice the distance. Your hand goes 1 meter, the box goes 2 meters. Maybe that's important to you. Maybe that's necessary. Okay. All right, let's talk about some of the applications. One is banked roads. So here are some race cars going around a track. They have very severe banked roads. That enables the race cars to take the curve at a higher speed than they could normally, because they're not relying on only friction to get through that turn. Some of the normal force, let's take a look at a banked road. Your car is here. Your normal force points this way, right? Well, the weight of gravity is here. There might be some friction force. If you're going really, really fast, there's some friction force in this direction, right? And what you want to do is think about what is our coordinate system here that we are interested in. This is a circular motion problem, right? The car is going around a circular track or a circular section of the track. And so the center of the circle is this way. And so we want our coordinate system to point in the direction of the acceleration. We want this to be our coordinate system, not the angle of the incline, because it's a circular motion problem. So we can split up our normal force into a normal force in this direction, the radial direction, and a perpendicular. And we can split up our friction force into two components. So you can see that by banking the road, we actually are gaining a lot because we're using the normal force, not just the friction between the tires and road. We're using the normal force to keep the car moving in a circular path. And so the car can go much faster around that bank turn than it could if it was going on a flat surface relying only on friction. So this normal force starts to add into our force needed to keep the car moving in a circular path. Now, I was telling my son that we were talking about race car tires. He's really into Formula One racing. And he reminded me that I forgot to mention these Formula One race cars are so light that they really don't, even though they've got these sticky tires that have coefficients of friction more than one, it's not enough. They need a bigger normal force. So they've got those Formula One cars actually have almost like wings on them, these airfoils that guide the air over and create a downforce. So in an airplane, those wings create a lift, right, that lifts the airplane off the ground. In the Formula One cars, they reverse them so that they create a downforce, and they press the car down into the ground to increase the normal force so that the tires get much better friction force with the ground. And they can adjust those. And I am told that they've done the calculations and they can actually create more downforce than gravity. So theoretically, I don't think it's ever been done. Theoretically, they could drive one of those cars upside down on a ceiling somewhere if they were going fast enough, because they create, with the wind creates more downforce into the ground than the force of gravity does. So anyway, a little more physics on racing. Question about friction force. I'm assuming that this car is going really, really fast around this bank turn. If it was just parked there, or it was going slow, the car, gravity would want to pull the car down the incline, so friction would be pushing up the incline. But if the car is going super fast around that turn, right, its inertia wants to make it go out to a bigger radius. Something has to push in on it to keep it moving in a circular path, to keep its radius the same. And so friction would be down the incline if the car was going fast enough. Okay. Think about what would happen on a flat turn. Maybe if you're having trouble thinking about friction here. On a flat road, your car comes along and makes this turn, right? Friction points toward the center of the circle, right? Keeping your car, pushing in on your car, keeping it moving in that direction. And the same thing happens here. The car wants to kind of go up to a higher point on that incline if it's going faster and faster, and friction is pushing down. And so we have N radial plus. Actually, we'd have to break up the friction force also, wouldn't we? So this problem gets complicated pretty quickly. Usually in physics textbooks, if you see a banked road, they tell you it's frictionless. So you're assuming maybe you hit a section of banked road in the winter time and it's iced over, and you can call it zero friction. And then the problem becomes much easier. You don't have to worry about the friction. But you actually would have to break up your friction force into a radial component and a perpendicular component. So by banking the road, you're actually reducing the friction force acting on the car. You're only looking at the radial component of the friction force. So you're reducing its effect, but you're adding in this massive component from the normal force, right, which is big. And so that's why banked roads are so helpful. You could actually, in a banked road, you actually could go around the turn with no friction between your tires and the road, because the normal force would provide the force necessary to keep your car moving in a circular path. Okay, so why don't we take a break here? We'll pick up with applications of the day when we come back. What force would cause? Well, the car could theoretically go fast enough where even the normal force and friction isn't enough to keep it moving in a circular path, and it would slide up the incline right in this direction. If it's going too fast, it's going to slide out up the incline in that direction. So you have to still, there's a balance, right? With the centripetal force, some of the forces in the radial direction equals mv squared over r. And so there's a balance there. Even with the normal force and the friction force, the car, there might be a speed that is too high that even the normal force and the friction force combined together could not keep the car moving in a circular path, and the car would slide up the embankment. Okay, 10 minutes. We'll come back in 10 minutes. Okay, we're back. Applications, circular motion. So we're talking about banked roads, common problem in physics books. As I said, usually in the physics book, you'll see it without friction. It makes it a little simpler to go through the thought process there. And satellites move in circular motion, and there are different orbits that you can use. There's a lot of satellites that orbit around the equator of the Earth, and we will learn in the last week of the quarter, we'll learn about geosynchronous orbit, where if you pick the right distance from the center of the Earth, your speed has to be just the right amount because of the force of gravity there that's acting on you. Your speed has to be just the right amount, and it will match the time it takes you to do a revolution is the same amount of time as the Earth to do a revolution. So the satellite will always be above the same location on the Earth, which is important because when you aim your satellite dish, you don't want to have to get up every 10 minutes off your couch and reposition your satellite dish because the satellite's moved in relation to Earth. It should always be in the same place with respect to the Earth. So your dish just gets set and you don't have to worry about it anymore. So we'll learn about that. But there's also a polar orbit. I was listening to a podcast one day, and they were talking about a company that had put a satellite in orbit to take pictures of the Earth. So they put it in the lowest possible orbit, so just above the Earth's atmosphere, right? If it's in the Earth's atmosphere, then it's going to burn up, right? It's just going through the air resistance. It's going to slow down and it won't last very long. You have to be just above the Earth's atmosphere so that you can give that satellite a push and it'll keep moving in that circular path around the Earth. But it does a polar orbit because the Earth turns on its axis, and then the satellite is going around the poles like this, taking pictures, click, 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 and the Earth is turning as the satellite is going around taking pictures, and the satellite can photograph the entire Earth that way because the Earth just keeps rotating. Every 90 minutes, the satellite completes an orbit, and then it goes around the Earth again, and again, every 90 minutes, it's completing an orbit around the Earth, and the Earth is rotating, and it's taking those pictures. Circular motion. And artificial gravity, they've talked about this. The longer you're in space, the harder it is on the human body. The human body, the bones and muscles and the body need gravity to stay hard, the bones to keep the density up, the muscles to keep the muscle density up. If you don't have to deal with your own body weight all the time, your muscles and bones deteriorate fairly quickly. Astronauts that have been in space for some time, sometimes they can't even walk when they get back to Earth. They have to go through a training program so they can even just walk again. They've lost so much bone and muscle density. So having some kind of artificial gravity for a space station, if we intend to occupy it for longer periods of time, is important. And so there was a movie a long time ago called 2001: A Space Odyssey, and they had a space station there that had artificial gravity. How do they do that? You make a big cylinder. There's your space station, and it spins, it rotates like this, and people stand. Where do they stand? They stand right here, right on the walls of the space station. Because as it spins around, they're standing on the wall like that. That becomes their floor. And the floor has to push in on them. The wall has to push in on their feet to keep them moving in a circular path. And if you get the space station dimensions just right and the speed just right, it will feel just like they're standing on Earth. Okay? Now, it's hard to get those just right. It would probably be much less, but it would at least feel like there's some gravity holding them, some force holding them against the ground. Their ground, of course, would be the wall of the space station. So that's artificial gravity. And then this actually happened, I believe. So because of circular motion, you weigh less at the equator than you do at the poles, right? Because part of the motion is going into part of the force of gravity is going into keeping you moving in a circular path. You do the math, you'll see it works out. You weigh less at the equator. So I am told that there's some boat races, I think it's the America's Cup boat race, where it's advantageous to have a heavier boat. So they have an upper limit. You can build your boat up to some maximum weight. You can't be more. So of course, they try to build their boats right up to that maximum weight. And one country's entry, they built their boat right up to the maximum weight. Then they shipped their boat to where the race was being held, and their boat failed. It weighed too much. They had to rip stuff out of the boat to make it qualify, to make it lighter, because they weighed it near the equator where they built it, and they moved it to where it was being, where the race was being held, which was off the equator, and it failed the weight weigh in there. It weighed too much. And then roller coasters, we're learning about this right now, right? The when that roller coaster car comes down the hill and hits that vertical loop-the-loop, it's going really fast. So you don't want to have a huge force acting on the people, right? It would be too hard on them. So you have a big radius of curvature so that it's not overwhelming. The force isn't too much on the people to keep them moving in a circular path. Big radius of curvature right here. Big radius of curvature where the car is going really fast. But if the whole loop had that big radius of curvature, the car slows down so much by the time it gets to the top, there wouldn't be a force holding the people in the cars except for maybe their seatbelts, right? You don't want that. You want the people to be pressed into the car because of the circular motion. You want the car to be pushing them inward on them, right? To keep them moving in a circular path. That means the person is being pressed into the car. So even without their seatbelt, they're not falling out of the car, right? But if the radius of curvature was too big there, the car is not going fast enough by the time it makes it to the top of the loop. So you have to have the radius of curvature get tighter, get smaller at the top of the loop where the car is going slower to maintain that needed centripetal force. So most roller coaster loop-the-loops you see are teardrop shaped like this. They have a big radius of curvature at the bottom where the car is going really fast. And when the car slows down, they tighten that radius of curvature to keep the centripetal force on the people so that they are pressed into the car. Okay. Okay, where are we? Centrifugal force. Okay, so centrifugal force is the fictitious force. There's no such force. There's no real force, but it's this fictitious force that you feel when you are in an accelerating frame of reference. So let's step back from circular motion for a minute. Just think about what happens. You're sitting in your car at a red light. The light turns green. You hit the gas. I know you don't do this, but maybe you've been in a car where this has happened. And the car pushes forward. What does it feel like when you're sitting in that car? It feels like you're getting pushed back into the seat, right? You're not getting pushed back into the seat, right? Nothing's pushing back on you. The seat's not pulling back on you, right? But it feels that way. Why does it feel that way? Because your body has inertia. It's sitting at rest. It wants to stay at rest. The seat starts to move forward. Your body resists that. And in order to get enough force to cause your body to accelerate at the same rate of the car, you sink into the seat a little bit until enough normal force is generated that gets you accelerating with the car. You don't ever move backwards into the seat, right? If somebody standing outside the car watching you just sees the seat push you forward, right? When you're in the accelerating frame, you feel that opposite force because of the inertia of your body resisting the push forward from the seat. So now let's switch our gears to circular motion. It's the same kind of thing. You are in that amusement park ride. Let's draw a picture. So you're in the amusement park ride where the floor drops out, right? So this is the top view of the ride, and there's a person standing over here and up against the wall, and there's another one standing over here up against the wall, and the room starts to spin, and you get pressed against the wall, and then the floor drops out, right? And you're stuck against the wall. You've seen one of those. So what happens? You feel like you're getting pressed, like you're getting pressed against the wall. But you're not getting pressed against the wall because something's pushing out on you. You're getting pressed against the wall because your body has inertia. So at this instant, your body wants to go this direction, right? You have a velocity in this direction. And if the wall disappeared, where would your body go? It would go in that direction. But your body doesn't go in that direction because the wall gets in the way, and the wall pushes in on you and changes your velocity vector. And now you're over here, and your velocity vector is this way. Why? Because the wall pushed in on you, right? There was a normal force pushing in on you. If the wall wasn't there, you would have gone in a straight line. But the inertia of your body wants to go in a straight line. The wall gets in the way and pushes in on you, and you feel as though you're getting pressed out into the wall. But that's not really what's happening. Somebody outside looking in just sees the wall pushing in on you, keeping you moving in a circular path. So centripetal force and acceleration, that's the inward one, that's real. Yes, and there is no centripetal force. It's not a new force, right? It's the same ones we're talking about. What causes centripetal force? Friction between the car tires and the road when the car goes around a turn, right? Gravity between the Earth and the satellite when the satellite goes around the Earth. A tension in a string between a toy airplane and a string when you spin it around, right? It's things we already know about are causing the centripetal force. We just give it a special name because of this special value. We know it has to be equal to mv squared over r when something's moving in a circle. Coriolis effect is a little different. We will deal with that when we get to angular momentum, okay? It's more of an angular momentum thing. G's that a jet pilot feels. Yeah, so 1G is what you'd feel standing on Earth, right? So it has to do with your apparent weight, right? We know how to calculate apparent weight. So if a car goes down through a valley, the person feels heavier, right, at the bottom, and they feel lighter going over the top. A jet pilot, same thing. When they go through maneuvers, some maneuvers they feel lighter, other maneuvers they feel heavier, and it's their weight. If they feel twice their body weight, you say they're pulling 2 Gs. If they're feel 4 times their body weight, 4 Gs. And they can, I think they can survive a fighter pilot like 9 or 10 Gs, I think. I forgot what the cutoff is for most roller coasters. Probably 3 or 4 Gs, something like that. Okay. I think we covered these questions. "10 Gs can be fatal," it says. So yeah, but I think jet pilots can do that. They may have special suits also, these compression suits that prevent the blood from going into their extremities and things, but they also train for it. Okay. We are ready for the next segment here. Come on. There we go. Okay, this is we've got these 2 guys hanging from ropes. A and B. B is a little heavier. Motionless from a roof. What's the tension in A, the top rope? Use G as 10 so you can do the math in your head. I've got a poll here, sorry. What number are we on? 11? Okay, good. Everybody answered correctly. 1,600. So we add up same two guys, but we cut the rope between A and B. It says, what is the tension in rope A? I have to, hold on. Okay, I think we're there. It's just the weight of person A hanging on there, right? So 700. Newtons there. Okay, now we've got A and B hanging there, and we cut the rope above A. What's the tension in rope B? Okay, most of you had it. So if there's nothing to pull on the other end of the rope, you can't have tension in a rope, right? So the answer here is 10 newtons, right? You can't pull on one end of a rope and have tension in it. So if you have a rope here and you want to have tension in there, the person on this side is pulling with the tension T, and something has to be pulling back with the tension T on the other side, or you would not have a tension in the rope there. Yeah, they fall at the same rate, right? It doesn't, mass doesn't matter when objects are dropping. Okay. Okay, now we've got them. We're going to allow them to hang this time from the strings. I'm not going to cut any strings, but the whole platform that they are attached to is accelerating upward at 2 meters per second squared. Says, what's the tension in rope A? Okay. Looks good. Excellent. So what are we doing now? We are adding up the, we know what the acceleration has to be, right? There has to be a force up on these two people. We know the sum of the forces equals ma. Call up my positive direction. So the tension minus the weight. I'm running out of room here. Oops. Sum of the forces, ma, up is positive, so that gives me tension. Minus the force of gravity. And the acceleration is 2. And so you get 1928, I believe. Is that right? So you're basically 12 times the total mass. Okay. Okay. What do we have? One more? Two more? Two more. 50-kilogram person stands on a 25-kilogram platform, pulling the rope attached to the platform using the pulley system shown. What force does he have to pull with to move the platform up at a steady rate? Use G equals 10. Okay. So we need to look at those ropes, right? How many ropes, how many times does the rope pull up on this person plus platform? And in this case, there are 3 times the rope is pulling up. So in our free body diagram for the person plus platform, we've got 3 tensions pulling up, force of gravity down. So the tension only has to be 1/3 of the total weight. Okay. Let's see if you've got that. So the person on the platform was pulling up on the rope. Now they hand the rope to someone else that's standing on the ground and let them pull on it. What force does that person have to pull with to move the platform up at a steady rate? Very good. We have 2 ropes pulling up on our platform. Tension here, tension here. The tension everywhere in that rope is the same. It's equal to the force the person's pulling down with. Some of the forces has to be 0 because it's moving at a constant steady rate. So we have 2T number 4. Because the person's not holding the rope anymore. So here the person that was pulling was part of the system. So we had three upward forces there. But here, the person that's pulling is not part of the system. There's only 2, the string is only pulling up on our system in 2 places. You're just looking at how many times does the string interact with the object that's being lifted. Only 2 times here. We okay now? We need another example. I'm sensing we need another example. How about we have 2 pulleys hanging down, And we run a rope. Where's our rope? We have a big box here. And our rope is going, is that what I want to do? Yeah, sure. Platform, what are we doing? 25, 50, let's make it 50. Person, oh. Let's call it M1 and M2, I guess. Okay, what's the tension in the rope? Yes. So the total weight down is 100 kilograms times 10 G. We'll use G as 10. About 1,000 newtons, right? That's 1,000. And so upward we have 1, 2, 3, 4 times the tension. Now if we, what are we going to do? Hand the rope to somebody else? Okay, I think we've got the hang of it. The string is only pulling up 3 times now on our box plus person system. So the tension in the string would have to be 333. Oh, I like that. So what are we doing? We're doing and there, this person is pulling on this. Is that what we're doing? So our string is that what you wanted? Exactly. Okay, so let's do this one. What force does the person have to pull with? I like that one. Okay, are we seeing it now? This is exactly like the previous problem. So here, when the person was holding it, right, the rope was actually interacting with the person and the box, or whatever it is, the platform, 3 times. Just look to see how many times is the rope touching what needs to be lifted. In this case, 3 times. So it's exerting 3 tension forces up. A rope can't push, it can only pull, right? 3 tension forces up, and we know the weight down was 750, so we could figure out the tension in the rope. In this case, the rope is only pulling up on on the thing we're lifting twice. So it has to be 2 tension forces up has to equal the weight of our object if it's not accelerating. In this case, the thing that we're trying to lift, the rope is touching it 4 places, pulling on it in 4 places. So we have 4 tensions pulling up. And here, it's only touching it 3 times, right? So we have 3 tensions pulling up. And now we want to see what happens in this case. So let's say, so the rope, we could break up this thing. We have a tension, and a, let's call that the pulling force, I guess. How does that sound? So what does the pulling force have to be equal to? Twice the tension in the rope, okay? Now, what's touching our system? Our system is M1 plus M2, right? We have a tension over here, that's this one. We have a tension over here. And we have a pulling force, right? And the pulling force is equal to 2 tensions. You could have just said, right? You could have just said this whole thing is my system, and I've got 1, 2, 3, 4 pulling up. But if you didn't see that offhand, then my way here is breaking it down a little bit more methodically, I think. So what is this equal to? This is F pull plus 2T has to be the total weight. And F pull is equal to 2T. And so T is 250. All right, so if you break it up, well, it's the person and the block, we're treating the person plus the block, right? M1 plus M2. Person plus block is one big thing. Right? Person and the block are, okay, good. All right, that was good. How about one more circular motion problem? We've got a object on a string, and it's moving in a circular path, a horizontal circle. So like this. A horizontal circle. Radius r, angle theta. So if we're given the length of the string and the angle, find the velocity. Have you drawn a free body diagram for this object? What coordinate system are you going to use? This is a circular motion problem, right? So what direction is the acceleration? Toward the center of the circle. So the acceleration is in this direction, right? So we want that to be one of our directions and perpendicular to that to be the other one. So we want to break everything up into components that fall in that. So the weight is already in that coordinate system, but my tension, I have to break that up into a t, let's see, this would be theta, I think, right? A t cosine theta and a t sine theta. Think about what direction your acceleration is. That's almost always the direction of one of your directions that you want to choose, and then perpendicular to that is the other one. All right, so what do? We say sum of the forces equals ma. That's a vector equation. We can split that up into sum of the forces in the radial direction is m times a centripetal. Toward the center of my circle is where I like to pick my positive direction. And sum of the forces in the other direction is 0, right? There's no acceleration in that direction. So the perpendicular direction tells me that t cosine theta has to equal mg. And the other direction tells me that t sine theta has to be m v squared over r. And so I can combine these two equations. I get tan theta. If I divide one by the other, I get tan theta is v squared over gr. And we're doing this direction is my radial direction, right? And this direction is my perpendicular direction. Now, r was not given, but L was, so r is L sine theta, right? So now you can just plug that in, tan theta and solve for V. Where are we? T sine theta. Just have to look at your picture. So here's theta. That means that this angle is also theta. So the adjacent side of this triangle is the cosine. Just look at the triangle. Adjacent over hypotenuse is cosine, opposite is sine. Don't think one is x and one is y. That'll mess you up every time. Adjacent and opposite. Here, I just divided one equation by the other, but you can substitute in the same way, right? You can say T is mg over cos theta, and then stick the T in over there, and you get a sine theta over cosine theta times mg, right? Good. Okay, I'm going to stop the recording. I will stick around if you have questions. I'm happy to go over them. And of course, we have our office hour at 4 o'clock.